All right. Thanks everyone for joining us for the third in the Q1 Space Underground Speaker Series. Today we're talking electric propulsion with someone that I've known for the past few years, Mike Holmes. I've known him in his capacity as the Director of Propulsion at EOI Space, formerly Earth Observant. Before that, I noticed in your LinkedIn bio, Mike, you claim to be unretired. So I guess you retired fully from like 40 years at AFRL, doing mostly EP stuff. It looks like. So I will let you kind of give us that history and get right into the presentation. And the presentation, feel free to correct me, but I believe it's a survey of different EP types and technologies that we could be going after.
Yeah, thanks, James. Although I have to correct you on one thing. It's only 30 years, not that old. So,
okay.
No problem, though.
Yeah. Well, you can fit 40 years of experience in 30 years' time.
Yeah, there you go. I worked enough overtime, that's probably true. So anyway, this talk fixes a problem, or I attempt to fix a problem that has been existing in electric propulsion research for a long time. And that is that most electric propulsion people don't consider where they're going to get the energy from. And they don't look at better ways to use the energy and better ways to get higher power. So EP has had a limited role in space for the United States mostly, and other countries partly, because we don't have the power systems and the energy collection systems that can drive them as hard as they should be to make them really work, to get the full promise from those technologies. So, and a good example of this is if you've seen the television series The Expanse. I love the way that story does it, and the book that goes with it. And it's science fiction, but it's science fiction based around a premise that is believable. It doesn't violate physics for the most part, at least not in the first year or two of the series. And basically, my talk that I'm going to give you today would be totally irrelevant if, like in Expanse, we could do fusion energy sources for propulsion. We can't do that. We're stuck with spacecraft that might give you a few hundred watts, maybe a few kilowatts if it's a big spacecraft, and you just can't drive much in the way of electric propulsion with that. So that was how this talk and this research that I've done for the last 15 years or so started. And you can see that if I can get control of my mouse, nope, sorry. Hopefully nobody gets seasick while I do this. This is a presentation I actually put together when I worked for AFRL. I didn't have time to generate a new one, but I think this talk is still relevant in that sense. And it actually started almost 30 years ago, working with a guy at AFRL back when it was the Air Force Rocket Lab called Dave Perkins. And Dave was looking at how do you better use EP if you use batteries. But all we had back then was NiCads, and NiCads really suck. It wasn't until the lithium ion came around that this sort of idea came about where we could do better propulsion by using batteries. It became practical, and by then Dave had retired, so I'm carrying on his ideas in this. And just a warning about this, there's a bunch of slides in here. And actually, James, if you can give me a 10-minute warning, because I think I want to have expanded question time if possible. I think that's more useful because I don't think I can get through all these slides. There's too much stuff I did in here. So basically, I'm going to show you how I compare different EP propulsion systems and with different metrics, performance metrics. This is looking at LEO to GEO type orbit transfers because that's what the Air Force was interested in. And so that's what I targeted. And yeah, let me dive in. Instead of telling you what I'm going to talk about, I'll just talk about it. Okay, so this, we're going to share these slides. So I'm not going to talk about every point in this. You can read better than I can talk, I am sure. So the basic idea is that if you have more power, if you can say use lithium-ion batteries that allow you to use a larger thruster, a larger EP thruster, right off the bat, you increase the efficiency of the propulsion system. For example, a 200-watt Hall thruster has about 20% lower efficiency than a 10-kilowatt Hall thruster. So by using a battery, I can drive the thruster higher power, and I get better efficiency out of the thruster. What's more, for the same delta V or same total impulse that you want out of the system, you operate the thruster for less time. And Hall thrusters and other EP thrusters, they don't, the size of the thruster doesn't change the lifetime much. They're all limited by about the same lifetime. So a bigger thruster means you fire it less, lifetime issues become smaller. I don't think we can save NASA interplanetary missions with that, because that's a different kind of mission entirely. But for things around Earth, and maybe for around the solar system, that's a big help. The other thing that's a big help around Earth is the fact compensates for the fact that orbits are so short, and the most efficient way to do a transfer is by a Hohmann transfer. So for the LEO to GEO transfer example, if you can do a Hohmann transfer, it's about 15% more efficient in propellant and energy if you do Hohmann over a spiral transfer. And you can do this with a battery and a bigger thruster. And I have some plots coming up. So that's the basic idea behind all of these slides. And so let's go on to the next one. So this is what the propulsion system looks like. I don't know if you can see my pointer. We couldn't get it to work earlier, but the diagram, I think, is clear. It looks like the power and propellant, the power line is broken in this. I'm not sure what went wrong with this PDF, but you have the spacecraft. And what I've done is I've put a battery between the spacecraft and the EP system. I've also attached an auxiliary PV array. So that's the other technology that has improved since the 90s, is that there are very lightweight PV arrays that in the 90s we couldn't even imagine would exist. But they exist now. And you can deploy them, and they're huge, and they're very light. So EP needs to catch up, and so that's what this architecture is trying to do, is trying to catch us up. Okay, so a lot of this is repetitive, so I'm not going to go to it again, but two different spacecraft on the left. One's a conventional system, where you use a chemical propellant. You need a lot of propellant because the specific impulse is low. And then once you get to orbit, the current use of electric propulsion is you just use it for maneuvering once you're already in your orbit. So for the LEO to GEO case, you probably would do station keeping to keep you at geostationary orbit. And so you get whatever mass is left over after you use this huge amount of propellant mass to get you in the first place. So the bottom one looks at what happens if you throw in a battery. You get a penalty for the mass there, but you need less propellant overall because the higher specific impulse. And so you get to your final orbit with more propellant, more maneuvering capabilities. So that's what I'm shooting for. So on the top right is an orbit transfer scenario for a chemical system, a large chemical system, where you do a perigee burn. That puts you in an elliptical geotransfer orbit, and then you do an apogee burn to circularize to get to a geostationary orbit. And there's some numbers there. And with chemical systems, you have a lot of power, obviously, because it's stored in the chemicals. So the way you have to do it with an EP system, even if you do have a larger array and a battery, is you have to do this in steps. So you do a perigee burn that raises your apogee a little bit. You wait, you come around, you do another perigee burn that raises your apogee a little bit. And you keep doing that. And so this diagram breaks out the orbits big enough so you can see them. And in the following plots, you're going to see there's a lot of orbits to do this. But this approach allows you to do a Holman transfer with an electric propulsion device. Conventional EP systems now, the thruster's a lot smaller because you can't provide much power. You pretty much have to do a spiral. You can't do a Holman. So the battery lets you step up to enough power that you can do Holman transfers. Okay, sorry, I'm trying to find my mouse. Here we go. Okay, so this is an example which I would really like to be able to point at, but we could not get the pointer to work right. But this is a real example. The battery is 7% of what I would size the battery for. And the way you size this is you want to collect all the energy in all the orbits so that you can use that energy for thrust. So this whole concept works because you only thrust part of the orbit, which means you need to store energy for the rest of the orbit. Otherwise, you're throwing away energy. So you can see the green circle in the middle, at least it's green on my monitor, is the Earth. And you start with a low Earth orbit at about 500 kilometers. And the red signifies the burns. So you can see I'm burning most of the way around the Earth with this concept. Then you coast, charging the battery, and that's that green color. And then eventually you fill up the battery if it's not big enough to store all the energy, and then you coast without charging, without thrusting, and you wait till you get back centered on perigee again, and then you burn. You just keep doing this until you get to apogee, and you can see the red region up at the top there, on the top left, sorry, and where you start doing the apogee burn. So there's a whole bunch of series of burns there, and there's a lot of orbits, so everything lands on each other, so I can't really show the separation between the orbits. So I do a small battery on this largely because you can see what's going on with the mechanics. The red orbit, you can see as I'm doing my burns around perigee, the perigee is actually increasing. So this isn't a very good Holman transfer, but it's still a Holman transfer. So I'm going to go to the next slide where I've got a bigger battery. This one is about 40% of the PV energy that you would collect in geostationary orbit. And you can see the orbits are further apart, and the most important thing to note here is that because I've got a larger battery, I can do a higher burn rate. You're limited to how much power you can put in the thruster by how fast you can discharge a battery, and I was trying to keep that down to about 0.5 C. But that's enough that you can see my Holman transfer actually is pretty good. My perigee isn't increasing much on the perigee burns, and my apogee is not changing much on the apogee burns. So that's another way of saying that I'm minimizing the gravity losses for the orbit transfer. And this is what an orbit with a battery big enough to do 100% energy utilization would be. So that the battery for this series of orbits is big enough that at any point in the mission, I waste no solar energy. Everything's either going to the thruster directly or going to charge a battery And that gives you the shortest amount of time. The only downside to this is that batteries right now aren't light enough to quite do this much power, or at least that was the case 4 or 5 years ago when I originally generated this presentation. I really need to update this. I don't know what the specific masses are these days on the batteries. Okay, so now let's go look at thrusters. Actually, are there any questions at this point? Is there a way for people to ask questions? Because I'm going to segue into thruster technologies now.
Yeah, we could either do questions right now, or we could put them at the end. I think Brian has a couple of battery specific questions that if we could keep to a couple of minutes would probably be good. So I'm going to read off the first one. Do you find it worthwhile to fly multiple batteries? And he's got more for later. But do you find it worthwhile to fly multiple batteries, e.g. a system for vehicle subsystems and nominal mission activities, and a separate battery for the EP?
Yeah, I would do. I'm sorry. Were you done?
Well, or is it better to have a large single battery?
For the purposes of this study, it made a lot of sense to use separate batteries because that way I'm not interfering in the spacecraft operation space in the study. And it's easier to do it this way for when I'm trying to educate spacecraft people that might want to use EP. It's easier for them to split out the impacts of larger arrays, larger batteries if they're separate. So that's a decision I would say would have to be made on a spacecraft to spacecraft situation and different and depending on the different missions. It is nice to deconflict. Another advantage that I didn't mention because it's relatively minor is by having a separate battery, you can deconflict spacecraft propulsion operation from spacecraft activities to a large degree, and if you combine the batteries, that might cause troubles there. So I guess the basic answer to that question is it depends, and that's beyond what I could answer in this type of study. Sure. But the reason I did it here was just to simplify the analysis.
Is there? Okay, and then Brian's saying, okay, so using multiple batteries because it's easier to separate out impacts and present that to other folks. So, are there efficiency issues in doing that? There are certainly mass impacts for having two separate battery systems.
Yes, and that's another reason to have a dedicated propulsion battery. We're talking about pretty high currents compared to what a spacecraft would typically require from a battery. These Holman burns at perigee are going to be on the order of 20-30 minutes, which means you could be pulling. It really depends on the size of the spacecraft, but you're pulling a lot of power compared to what the spacecraft would usually use, which means you're going to have large conductors, which means you're going to want the battery close to the propulsion system. So that's another factor you would have to look at on the spacecraft. Separating the batteries, there's a good chance separating the batteries will make life a lot easier.
And then can you comment on, at this point in your presentation, any distinction between LEO versus GEO versus lunar versus interplanetary operations?
Yeah, so for LEO operations, the Holman transfer only helps you a little bit. If you're just going up and down a few hundred kilometers, your orbits are nearly circular. That doesn't help you much. If you're doing interplanetary, if you want to escape Earth, the savings by doing the Holman transfer actually comes out close to 60%. So there's a big advantage in that case for escaping Earth. Once you get around the sun, the perihelion times are so long it's not clear to me that a battery helps you much. In that case, having larger arrays is what you want to do. So that changes the story entirely. Since I was working at AFRL, the Air Force, at least at the time, was really only interested around Earth. And Earth's a deep gravity well. Everything changes when you're around other bodies. The moon, you could go from LEO to moon orbits with a lot less propellant and less time than you could with a conventional EP. We're still talking fairly long transfer times compared to chemical, however. So by using the battery, larger arrays, we should be able to do 2 or 3 month transfers instead of years for spiral transfers. That starts to become more attractive. If we get better batteries, which I assume we are, things really start to look a lot better.
Cool. Okay. I think I'd say let's move on to the thrusters.
Okay. So in my study, I do some analysis, some performance curves based on different thruster technologies. So there's electrothermal thrusters, which are like arc jets, Hall thrusters, which are very efficient, make those attractive. Electrospray thrusters, which have some nice features, but they have not yet been scaled up large enough to be all that useful yet. And then electromagnetic concepts, which are very attractive, but those especially probably need high power to become really efficient. So I think I said 20 kilowatts somewhere in here it'll come up. Let me just go on. So here are those concepts drawn out in picture form. So there's the chemical thrusters upper left. They're electrothermal, use isentropic expansion through a nozzle. You're basically limited by either the flame temperature of the chemicals you're using or the materials of your nozzle throat, which will tend to melt, or how well you can cool the nozzle throat. So that limits a specific impulse. So hydrogen, oxygen rockets do best here, about 450 seconds ISP. Then there's electrothermal thrusters where you use some sort of resistive heating. Arc jets actually flow current through the propellant itself to heat the propellant, and it's isentropic expansion. You can get a little better with arc jets because you can you're not limited by the chemistry, only the materials. Excuse me. And your specific impulse in both of those is proportional to the square root of the temperature. Then you have the electrospray thrusters and the Hall thrusters, which are electrostatic in nature. So the specific impulse in those cases is proportional to the square root of the accelerating potential over the mass of the ions or the particles that you're accelerating. So that's what limits those. Hall thrusters, of course, are very efficient, as high as 70 to 73%. Some people report in the right regime, and they also scale up nicely. The bigger they are, the more power. So there's 100 kilowatt Hall thrusters being tested these days, and those will work really well. And then off into the future, electromagnetic thrusters, the lower right, I drew a picture of an FRC thruster. And those thrusters move back to essentially isentropic expansion. But the nozzle is magnetic so that you don't have to worry about melting the nozzle. It's a magnetic field. It doesn't care about temperature. So that takes off the temperature limit on those. And those devices, in principle, could go to very high specific impulses, or you could run them at lower temperatures, lower specific impulses, and get higher thrust to mass ratios out of them. So those are very promising. They take a lot of power before they become efficient. So most of the laboratory work has been very low power, so they haven't performed well. And the problem there is if you have a 5 kilowatt electromagnetic thruster, for example, and it only does 20%, it's hard to get funding to scale that up to 100 kilowatts. 10 minutes left? Okay. So by the way, we're going to share these presentations. I'm not going to make it all the way through, obviously. So basically, I'm just describing what's in here. So I'm going to move on. So these are some of the curves that I've done, different metrics. So I've done different specific impulses. And let's see, this particular chart is for hull thrusters. And the top, I'm just going to describe the top one. There are 4 different metrics I'm comparing, but once you see the top one, it's easy to figure out what the other ones show. So the top one, there's a dotted line across the top that corresponds to the trip time for a spiral burn scenario that typically done with hull thrusters. Hull thrusters are also nice because they're throttleable. So you can crank up the mass flow rate, the ISP goes down, but you get a better thrust to power. So you can see the green curve. You can drop the trip time down considerably by operating at a lower specific impulse. So in combination with the battery doing the Holman transfer, this is how much you can reduce the trip time. And then the plot before that is the acceleration that you can get once you're to your destination. If you discharge the battery a single time, the third plot down shows you how much delta V you can get. And then the fourth one down is the delta V once you're in the orbit. I think I misread one of those. Second one is the acceleration available once you're in orbit. I may have said that wrong. And then the bottom 2 plots just give you some idea of how the dry mass changes with the battery mass and the thruster power to mass ratio of the propulsion system. By the way, I don't think I said this before, but all those orbits, those are actually solutions to Newton's law. It's an integrator. Okay, so with the amount of time I have, let's see. So this is a very useful plot that shows a comparison of a bunch of different types of thrusters. So on the right side of this, along that blue curve, that is hull thruster technology, and hull thrusters are terrifically consistent. High efficiency. This is thrust to power. As I said before, this is the most useful metric to doing orbit transfers. And then I've got efficiency lines that go along on top of that. So there's chemical thrusters in here. So I converted chemical thrusters to thrust to power by looking at the energy contained within the chemicals. And then I have an electrothermal model, hull model, electrospray model that are fit the best I could to those data. Some of that data is very sparse, so you have to wonder about my fits, but it's what I could do. So that's in here. And then my next few charts, I show how those different things perform. And I think I am pretty much out of time. So this is a delta V at the mission orbit. So you can see a bunch of different curves showing the delta V capability versus the ISP you use in going from LEO to GEO. So basically, I think everybody's going to have to be on their own to look through these, or you can always contact me, ask me more questions if you like. I've got a slide on technology limits.
Mike.
What's that?
We have 5 minutes left here if you want to pick another page or two to just highlight. Otherwise, we can move into the Q&A, and some of that might be in there as well.
Yeah. Let me go to my conclusions, and you can if we do questions, I can go back and look at those plots. It's kind of a bludgeon of a presentation anyway, so it's the sort of thing you really probably want to look on your own. So my analysis, I didn't find anything new. It's pretty consistent with previous mission analysis, what little of it's been done on this type of thing. Energy storage does show advantages. The whole thruster performance seemed to be the best for using battery and PVs, and that's essentially because it's a very efficient thruster for the power range that we're talking about. We can indeed, with higher ISP, give more capable than chemical. That's no surprise. Another thing that could be looked at that I did is carrying a small chemical thruster. That's more of an Air Force thing where they feel like they have to move really fast to avoid something hitting them. And the trip time is still the biggest concern. And that's the biggest concern because it would still be nice to have a little bit better batteries and a little bit PVs. But I'm hoping in the end that this analysis will encourage people to really think about how to use the newer energy technologies that are available. We're not going to improve Hall thruster efficiency much with research on Hall thrusters. It's time to start looking at the energy. So I'll stop there and take questions.
Thank you, Mike. I'm gonna stay off camera because my bandwidth is struggling. I think it's time for a new router because I should also have pretty good internet. Anyway, I don't know if there's any questions from the audience. If anyone wants to speak up, otherwise I think we have a backlog of Brian Sims questions to move through. Yeah, okay. I think he's indicating he and I am also really curious. Have you considered nuclear thermal propulsion as a part of maybe not this presentation, but just kind of stuff you've been working on?
Yeah, there's a lot of people working on nuclear thermal. That's a good way to go. It's got all the headaches with nuclear. I'm assuming he means nuclear fission. But yeah, that's a good way to go. And nuclear electric fission power for electric has also been looked at. The thing that usually kills that concept is the mass of the reactor. And I think that's the future around the solar system, personally, is fission. But I also think we're probably going to have to go to asteroids and places like that to find the nuclear materials because it's pretty tricky launching stuff off of Earth. There's ways to do it safely, but the public acceptance of those ways is tricky too.
Sure. Let's see. Anyone else? So I'm going to read another one off here. Leo seems like a no-brainer for efficiency with station keeping and moving between orbits. Geo seems like a no-brainer for efficiency on station keeping. Lunar and interplanetary seems like a huge win on reducing propellant needs. So it's sort of like a trade-off between how quickly you can actually move. Is that your feelings on that as well?
Yeah, it's a trade-off how fast you can move. It also a trade-off on propellant mass. You reduce the propellant mass a lot by doing those things. And right now there's a benefit. I mean, you can do 2 or 3 month transfers. It would be nice to go faster. But with better technology, with improved battery technology, if it continues to improve like it has, not only will these propulsion systems work better, but we'll probably all be driving electric vehicles by then. So,
Sure. There's an addendum here. As we move to a lunar economy, it seems unlikely that we will long-term find it cost-effective to refuel chemical prop systems. Although there are a couple of companies working on in-orbit kind of servicing. There's a simplicity associated with chemical propulsion that is reminiscent of the simplicity that's available associated with an internal combustion engine, and kind of why they've hung on for so long. So, and there's a supply chain and a market and an understanding. So do you feel like that's a fair comparison?
yeah, not quite, because internal combustion systems are extremely complex and were developed very slowly. It's taken decades to get where we go now. They work really well, but the original ones did not work well. Electric propulsion systems are much simpler. I just bought a Rivian, and that thing is so much simpler than an internal combustion engine. And I don't have to worry about lubrication, or not nearly as much anyway. And a lot of things you don't have to worry about. So let's see. I think I've lost track of the full question.
Yeah, do you feel like there's an inertia behind, widely adopting EP for in-space?
Yeah, there is. There's a lot of resistance, especially in the primes. They want to do things the way it was done before because they have shareholders. They don't want to try new things, and this is a struggle I had at AFRL, where I was generating requests for proposals and SIBR topics and stuff like that. We could do that for the technologies that would advance these things, but the primes did not want to move to something else. So it's a similar sort of resistance we're seeing now, going from chemical to electric. I remember the other thing too, though. There are resources in space, more on asteroids than the moon. But asteroids, comets have a lot of stuff that could be used as propellant, and that would also change the way we do things. Probably the most important volatile that could be mined in the solar system is water. And propulsion systems that use water would be the way to go, which would probably be electromagnetic. So that's where I see the future going. If we don't do fission power, if we don't do fusion, then large solar arrays with water mined off of asteroids is my suspicion where we would go. We would use electromagnetic thrusters, MPD thrusters, things like that. And when you think about it, that is fusion. The sun is a fusion energy source that we can collect with solar panels. So unless there's a breakthrough on fusion, I think that's where we're going.
Okay, so what does MPD stand for?
Oh, I'm sorry. Magnetoplasma dynamic thruster. It's just a class of electromagnetic thruster. So,
you crack the water thermally and then direct that, or how does that work?
You would do an electrical discharge through the water. It vaporize it into oxygen and hydrogen ions and a bunch of electrons. And there's different ways to do it, but most concepts, you magnetize the electron cloud around that, and then you push off on the electrons magnetically. The ions all have to follow the electrons, and that means you're moving the propellant in bulk, as opposed to ion thrusters where you're accelerating the ions and you get a differential acceleration. So this gets really complicated in the physics, but the electromagnetic lets you electrically push bulk plasma very efficiently. But it takes a lot of power to break down the propellant to begin with. And for small scales, it's very inefficient. For large scales, it becomes much more efficient. So I think we're looking at 100 kilowatt class things at minimum, probably megawatts. So good luck finding a contract from the government to have you do 1 megawatt.
If you know where I can find one, that sounds like a worthwhile pursuit.
I'm sorry, I didn't hear you, Jay.
If you know where I could find one of those contracts, that sounds like a worthwhile pursuit.
Yeah. NASA actually had a 100 kilowatt competition. I think it's probably been like 10 years ago. So a long time ago, and I haven't heard of any since. But it's time. Maybe we need to all write our congressman.
Yeah. Okay, I'm gonna Brian, if you're in a position to jump on, I'm just gonna invite you up because you don't need to have this conversation through me. So I'm gonna invite you to the stage and see if this works. Here we go.
Hello. How are you, Mike? James?
Doing good. I can hear you.
Good. Yeah, so I mean, I've just been kind of going through, and as you've been talking, I've had some questions, and I've had some other questions kind of rattling around in my brain for a while anyway. But there are a couple of things you mentioned that seemed interesting, and my first question was really about from a longevity perspective, including refueling. What do you buy with an EP system that you don't necessarily have with a chemical system? And just, are there durability benefits you get from an EP system? Are there less, as you were saying, with an ICE engine versus an electric motor, you get simplicity. So there's fewer parts, so there's less to go wrong. Do you have similar types of is there an analog here for electric propulsion as well?
Yeah. Take a Hall thruster, for example. There's no moving parts. The cathode's kind of a headache, but by going to larger powers and shorter total run times, those lifetime issues pretty much go away. Unless you're NASA doing interplanetary, then that's there's other things you can do with that. It's one thing that I didn't get a chance to talk about is the missions are extremely complicated doing these multiple Hohmann transfers, though. You've got to control the spacecraft every time you come around perigee. The burn arc has to start in a different place and end in a different place, and just doing the analysis I did was much harder than I thought it was going to be. So it'll take some time to really implement that. That part is quite complex.
Okay.
And a possible showstopper.
Are there things that we could offload, at least to some extent, with onboard, observables that the vehicle has that it could use to determine when it needs to start and stop burns or things of that nature?
Yeah, I think so. I think that's actually the way to go. I haven't put much thought into that, but yeah, automating, obviously, knowing when you're approaching perigee and when you're leaving perigee, and you can be a little bit sloppy. Earlier versions of my code, when I wrote the code, I have to tell the code when to fire. And earlier versions, I didn't do very good at that, and the perigee would shift around, and all sorts of weird things would happen, but it still worked. So yeah.
I mean, I know some of the Mars vehicles were doing aerobraking, and they were loading some level of autonomy to the vehicle to take care of some of that.
Mm-hmm.
So, it just seems like that may be challenging analytically up front, but it should be a one-time problem.
Yeah.
Hopefully.
Yeah, somebody just needs to put some thought into it, more thought than I've had time to do, but
Sure.
Maybe an Earth limb detector, because you can just look at the Earth to tell how far away you are, things like that.
Sure. Yeah, that makes sense. I think one of the other items that I guess I was wondering about, when we talk about electric propulsion, everybody's always talking about we're using this as our propellant and we're using the electrical aspect to make that better, right? Make the performance better. But when you start talking about scavenging in space, whether it's an asteroid or a comet or pick your favorite thing that you're going to go scavenge from, is there a way to genericize the propellant capability such that, I have a tank, right? Because I have to store it somewhere. How do I get something into the tank and maintain it in the tank? But are there ways to make that generic enough where we can take a whole class of things and store it in the tank? And yeah, maybe my performance changes a little, but maybe I don't care.
Yeah.
Right? There's ways to accommodate that. If you can refuel in flight, it opens up a whole bunch of different ways that you can now accommodate your mission design that are more flexible. And maybe you say, here's my bounding boxes of my worst case performance, my best case performance. But if I'm anywhere in this box, I'm fine. It feels like there's an opportunity there longer term where even if we're not able to refuel with something that's maximally efficient, if you have any vehicle that's going to be doing anything for any length of time in interplanetary space, having to carry all of the propellant with you is always the driving factor. So if I can just refuel, it opens up a whole bunch of new opportunities for mission design and what types of missions we could potentially fly that we can't do today.
Yeah. Yeah, there's a lot of work going on the in situ propellant utilization. NASA, I haven't looked in a while, but they used to have a lot of cyber announcements doing that kind of stuff. I even gotten in on a part of that with the company, and unfortunately, it's still proprietary. I can't talk much, but we were essentially just going to pick up rocks and throw them as fast as we could for propulsion. And unfortunately, I can't tell you how we were going to do that. There are concepts that have been proposed that use tethers, and you spin things around on the tether, and then you fling the rocks off. And there's all sorts of ideas because once you're out of a huge gravity well, specific impulse becomes less important. Sure. Or if you're around the sun, it's such a large gravity well that you have a lot of time to thrust. So it's going to take you a long time to get anywhere, no matter what you do interplanetary.
Yeah,
we do fusion. Anyway, sorry.
Right. Well, even if you're using fusion, I still think you've got limits, right? So you still have fuel, you still have to go and figure out what you're going to do with that. I was thinking from the standpoint of right now, every time we have a mission, we have to launch it from Earth, which is massive amounts of wasted propellant to get into orbit. And then we have to carry a whole bunch of propellant. And when we're out of propellant, we all say, oh, well, the mission's over.
Yeah.
And we could design vehicles, and we have vehicles that have been in space for a long period of time. If we weren't artificially constrained by the prop budget, you could do a lot more work in a lot of different places over a long period of time. If you could just say, hey, I'm going to go and fly around the asteroid belt, I don't need to send another vehicle because I ran out of prop.
Yeah.
Right? That's silly, but that's where we find ourselves.
Yeah.
So I'm just thinking longer term, are there ways that we could get to a point where we could kind of address that aspect of things and take advantage of electric propulsion for that?
Yeah. The best way I could answer that is to pick one example, which is water. There's so much water in the asteroid belt, and even in near Earth asteroids, and if you have water, you can either do the electromagnetic propulsion concepts, and there's so much water that you wouldn't even need super high efficiency, and you could do that. The other thing you could do, if we had a way to collect the water, and it's easy to collect water, it's in the form of ice. You land on an asteroid, you apply some heat, you capture the water that comes off. It might take some time, but there's a lot of water. And actually, that showed up in that science fiction series, The Expanse. That's what they use for fusion. And we could do the same thing. And if you have water, you can do electrolysis. It might even make sense to go to hydrogen, oxygen rockets at that time. Low ISP, but maybe we don't care. Maybe there's so much water in the right places that we don't care. That's a different analysis. I think there are people at NASA looking at that closely. So I can't answer it, but I think the answers are there. And personally, I was really disappointed when Trump canceled the program to bring an asteroid to Earth orbit because
A redirect mission.
a redirect mission, yeah, because that there was a chance we could look at getting propellants off that asteroid. Not to mention, rock makes a good radiation shield. If you want to make a space station where you're not cooking your astronauts, that would be a good way to do it. So anyway, now I'm getting into politics. Sorry.
We have one more. We got one more question in the chat, and then I think after resolving that, we'll move it over to the table, and I'll explain how to get over there. But last question in the chat is just, in your opinion, what's the biggest missed opportunity in electric or in-space propulsion that isn't in use today? That is, what could we be doing now, or has some economic or strategic utility that is just hasn't been explored or deployed?
I would say it's the power thing. Just looking at using modern power technologies, the propulsion community is 20 years behind, basically. So at AFRL, if I said, hey, we need to look at better power technologies, I got shut down because my manager would say, we don't do power, we do propulsion. Okay. And the same thing happens with people I knew at NASA. So there's pigeonholing of this is technology, not power. So I think that's the biggest lost opportunity.
So not treating it holistically.
Yeah,
As
you got to look. It's energy conversion.
Sure.
You're generating a beam of energetic particles to do propulsion. It's all energy. It's and people get budgets based on propulsion, not power in that community. And then if you go over, you talk to the power people, you get the same effect. They say, well, we don't do propulsion, so we don't want to make a power system that would work well for your propulsion system because we're a power group. So
makes sense. Or it doesn't make sense, but I can see how that might happen.
Yeah.
All right. Well, hey, Mike, thanks for doing this. I really appreciate it. I know our audience does. This is going to be available for watch and rewatchability up on YouTube. I will make sure to get this presentation from you, and we'll include a link to that as well, I think, and we'll put it in the Discord as well as a community resource, if that's all right with Mike. And I think that's the end of this broadcast. And Mike, if you just want to click on over to table 1, I think that's where all of us are going to kind of hang out and debrief for the next few minutes.
Okay.
So thanks again, everyone.
Yeah, thanks everyone.